So, what very short versus a very long have a dog that has some math with a this math is program and looking for this one. Uh, which would be faster? When the ball reaches the bottom, moving it from in the top, reaches the bottom there. My question is, which box is having faster at the bottom? What's the team going over? Does that matter? So they both start at the same height, 8. They both have a mass m. So at the very beginning, their potential energy is 58. And at the bottom, it's converted into kinetic energy, right? 1/2 is squared. Nope. Mass is on both sides, so it doesn't depend on mass. No. Where in this equation does it tell you how steep the slope is? Does the steepness of the slope is it anywhere in the equation? It only depends on height and the acceleration due to gravity. Velocity equals the square root of 2a. Only depends on the acceleration due to gravity and the height above the surface. So both of these thoughts would be traveling at the exact same speed at the very bottom. Does it depend on mass? Does it depend on the shape of the slope? In fact, I've drawn another one, actually another lap, that had one that did this. It came over, went down, did a loopy loop, came back, did this, and ended up right here. So the box in all this crazy motion would still be the same speed. Because at the very beginning, it started with some potential energy, and all of that potential energy is converted into kinetic energy, the conservation of energy. Now, what the difference would be how quickly does it take for the box to get down? You are correct. This one would get down the slope very fast, but this one would get down the slope very slow. But when it's at the bottom, speed. So whenever we have, for example, suppose we have this force, this starts at the height 10 meters. This starts at the height of 3 meters. I say the drop over the initial speed of 5 meters per second. How fast will the box move at this point? Again, this loopy loop doesn't matter because conservation energy. Here, so the initial energy will be equal to the final energy using more specific chemical energy. And the chemical energy will be the initial energy plus the initial energy equals to the final potential energy plus the final kinetic energy. So initial potential energy will be m times v times the initial height plus 1/2 mass times the initial velocity. There. Now we equal to m the final height plus 1/2 m the squared. One thing to note, that as long as the mass doesn't change, we see the same mass throughout the entire problem. So I can divide the entire equation by m, which means all these things wow, mass is not change. Because unless you have friction, if you have friction, then you max out, but everything accelerates at the same rate. Accelerates through the gravity rate mass. As long as the acceleration through the gravity is constant, you're not going from the surface of the earth or this. When we solve the df myself, and this number, so that is g is I plus 1/2 the I squared minus g is f to the 1/2 the squared multiplied with times 8 times 2. So that would be c plus the I squared minus g is f to the I squared. Then we take the square root of the equation, and we end up getting that the final velocity is the square root. Plus or minus, but for these problems, we don't have a correction. QG is I plus the I squared minus the f. We can do some factoring if we want. We know the problem is the numbers. That is square root minus 2 HI minus HF plus the I squared. So we get root of 2 minus 1 times difference in height, and the height, which is 10 minus 3. So we plus the difference in squared and squared. Minus 2 being the 34. So, I tell you in this practice, the students is always first. Energy is always conserved. It's only it cannot be created. If you want to study very, 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 very advanced physics, this is only true at time with time. Meaning that time is very so if the clock starts ticking more slowly because the time dilation, time goes out, energy is conserved. If space-time is expanding, then time energy is conserved. That's very advanced stuff. The reason for this is if you take a photon that moves across the expanding universe, it's redshift and energy is how much is related to its wavelength. So a photon going across the expanding universe would lose energy. But as long as you can solve for an equation that gives you the signal time, then energy is what we propose.
Regresó el único.
So here's a question. If I were to put a ball right here, where would the ball stop? And if I put a ball right here, where would it stop? So these are at the exact same height. Now this is a screw lamp, I mean real lamp. So we do have freedom, but
But this side is three.
you know that it has some potential energy stored here. As it goes down, some of the potential energy stored in it. When it's at the very bottom, it has the most kinetic energy, and as it starts rolling up the lamp, it's going to start converting from kinetic energy to potential energy. And the point in which all the kinetic energy is converted to potential energy is energy at height. Note that this is not a closed system, meaning that some of the energy is converted to thermal energy.
3 times longer than this side is. And so my first question would be, if I were to release the ball here, could it possibly roll off the opposite side? Well, let's give that a quick try. And we see it doesn't. How about if I try it from this side? And it won't do it from that side either.
So as long as this these two point pressure is that same height, there is no possible way to press as long as you don't push it. If you push it, you can get some energy and this is velocity to it. So if you give it some initial kinetic energy, you can go over. So you can get this is one of the most famous ones. This is very, very dangerous.
Believer of, I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided
want to
Take your seats. Take your seats, please. My lecture will be about 40 minutes. And after that, I will give anyone the opportunity to ask me questions for about 15 or 20 minutes. So the whole thing will be 1 hour. And it is after that hour that we will do book signing. You can buy the books there if you want to, and I'll sign them here. We'll get back to that later. Now I want to return to the conservation of mechanical energy. I have here a pendulum. I have an object that weighs 15 kilograms and I can lift it up 1 meter, which I have done now. That means I've done work. MGH is the work I have done, believe me. I've increased the potential energy of this object. 15 times 10 is about 150 joules. If I let it fall, then that will be converted to kinetic energy. If I would let it swing from 1 meter height, and you would be there and it would hit you, you'd be dead. 150 joules is enough to kill you. They use these devices, they're called a wrecker ball. They use them to demolish buildings. You lift up a very heavy object, even heavier than this, and then you let it go, you swing it, thereby converting gravitational potential energy into kinetic energy, and that way you can demolish a building. You just let it hit, and it breaks a building. And that's the whole idea of wrecking. So you are using then the conversion of gravitational potential energy to kinetic energy. Now, I am such a strong believer of the conservation of mechanical energy that I am
So it's moving with the greatest kinetic energy horizontal. So he walks within its regular line.
willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0.
Very, very dangerous, but physics. There's no possible way to harm you as long as you leave at 0 speed and get you, like I said, forward. Now, we've been dealing with work also. So, work only applies whenever it's directed. Here's a question for you. Do you have an Earth? And this is not the cell. Do you have the moon? And orbiting around the Earth. How much work is Earth for storing on the moon if you get orbiting? How much? Force, uh, displacement, Earth. So where's the displacement at? Yeah, no. Earth, the moon's right here. Eventually it'll be right here. So let's just look at it when going from here to here. So move from this place from this side. And yes, you're right, eventually it'll come back this way. But just looking at the time frame. Where's the force? The gravitational force is in this direction. And what angle is this? Roughly 90 degrees. Remember, the work, it must be parallel. Is this parallel? Perpendicular. So the total work, if the moon goes from here to here, is 0. That's because force and displacement are in perpendicular directions. Work only counts for whenever force and displacement are parallel or in the same direction. So you can work with an tired after leaving the moon. Actually not producing any work on it. I would say something else. So let's say that let's say we have a clock. It is moving in this direction with a velocity of 10 meters per second. And let's make this a 5 kilogram rock. And we're going to want to stop it within 15 meters. How much force is needed? How much force is needed to stop the clock? So if this is going to use the fact that work equals the energy. So you're going to be pushing on the block in the opposite direction. Your force is going to be in the opposite direction. Our initial velocity is 0 meters times 10 meters per second. Our final velocity, we're going to stop it, so it's going to be 10 meters per second. Or distance for the displacement is 8 meters. And so we have force times displacement equals to 1/2 df squared minus 1/2 m dr squared. Since df is 0, so we have d times displacement minus f times displacement equals 1/2 mass in the I squared. And it's also force is divided by displacement. Mass and velocity squared divided by the displacement for mass is 5 kilograms. This will be n squared divided by 2 times displacement in meters. And we get 25. So again, we could have used kinematics to solve this, but by knowing this alternative formula here, so we could have used kinematics. We don't know anything about time, so we would have to use dx squared because of d squared um, plus 2a delta x. And in this case, we can solve for the acceleration. The acceleration would be equal to dx squared minus di squared divided by 2 delta x. And we need mass. So we know that f equals ma. So we multiply both sides by m. A equals dx squared minus di squared over 2 x. 4. And this is 0. So force is equal to negative di squared over 2 x. So this doesn't equal delta d. That is not even. Haven't really covered too much power. So power equals energy time or work. Power is the rate at which energy is used. So let's say that you are working at a rate of 500 bucks for 2 hours, pushing a 5 kilogram. Assuming the clock is initially set, how far does it push it? Well, we know that power is equal to work time. Solving for work, we see that work is equal to power times time. Energy is also power times time. And we know that work is equal to force times distance. And I saw persistent. Distance you can use hours at a time. It seems to say assuming you push the constant. Then we have what? 2 hours. But you can look at the second. And get a crazy number, 300,000 meters. The efficiency is a measure of equal work or equal energy over total energy. The it takes energy used and energy that wasn't converted, energy that wasn't lost to heat over total energy. So, for example, uh, let's suppose that we initially do 50 joules of energy while pushing them off. At the end, we bought at 30 joules of energy because 20 joules was lost into the burden. How efficient are we? So you can either say 50 joules minus the amount of lost 20 joules is total 80 joules, or we can swap only use 30 joules, 30 joules, 50 joules, depending who are 40% of energy was lost in heat. This is what you see whenever you're buying things and you talk about energy efficiency. If something is 98% efficient, that means that it's 2% is lost in diffusion. There is only one thing in the universe that is 100% efficient. Not anything that we create. Space heater. Because it produces heat. So we have a space heater. Some of the energy is going to be lost in the wire. As we push electrons through the wire, as we push current through the wire, some of the energy is going to be lost in the heat. But we're on producing heat. So it's just how formula. Some of the energy is going to go into the motor from the fans. The fans will turn and slow down by air resistance. But when it's slowed down by air resistance, some of the effects of converting electricity to magnetism off. And when it's returning, it goes through the wire, and we still have there. But the whole purpose of the space heater is to produce heat, so it's 100% efficient. Note, however, electricity generation, if we were to include the electrical power plant, then we would produce much more. Because we can't produce electricity. Do you know what the maximum, most efficient thing in our universe? 43%. Conversion, 43%, and it's converting mass into energy. And you know how you do it? You take a really fast spinning black hole, rotating black hole, and what we do is we take a two-stage rocket and we go around the black hole and we somehow disconnect it in a certain special way that half the mass is going into the black hole and very complicated this mass is getting off. We can extract 43% of the mass we lost to the black hole, basically converting rotational momentum, extracting some of the rotational momentum. Besides that, so I want you to think about that. Even in the best nuclear case, breaking atoms apart, burning coal, doing all that, the most efficient theoretical way is keeping a giant rotating black hole and still get energy. It's very hard to actually extract the universe. The idea is more about this thing in the thermodynamics is why meaning that we're going to run out. And the universe is just going to keep frozen. People be able to what all of the when we go into thermodynamics and start doing more about work and physically there, in order for you to actually produce energy, you have to have a high concentration of energy, a low concentration of energy. And as energy goes from one point to another,